Great, so let's talk a little bit about the action potential. Here's a picture that probably looks kind of familiar to you. So when we look at these electrical signals in a neuron, what we're looking at are the ions, right? We're looking at a change in ion concentration across the membrane. So it's the electrical signals that really move a message down a neuron, down the axon. And what we see on the right here is just kind of the classic view of these different channels: potassium leak channel, a voltage-gated sodium channel, and a voltage-gated potassium channel. And this is representing the time point where a neuron is at rest. So we can see on the graph we have resting potential here. And then what we see is that we're becoming less negative on this graph. So that's implying that we have more sodium is coming in. So we can see that sodium comes in. We still have a kind of an exchange on the leak channel of potassium, but the voltage-gated potassium channel is closed. If you have enough sodium that comes in, then we're going to get a full blown action potential. So we hit threshold, we get the action potential. And then down in the bottom, what we're seeing, if I can move this a little bit, is we see the falling phase. So this is where this one had the sodium voltage gate open. Now this one has the potassium voltage gate open as well as this leak channel. And so what we see is this falling phase. We see potassium driving this activity when we see repolarization. So we have resting potential, depolarization, and then repolarization. So this talks about just what I said there. This idea of becoming less negative is something that is called depolarization. And we can see, though, that it doesn't always necessarily lead to an action potential. So when we have resting potential over here on these graphs is negative 70 millivolts, you can have activity on that postsynaptic neuron where something causes the sodium comes in through the voltage-gated, the ligand-gated sodium channel. You get a little sodium trickling into the cell body, and we get these little wavelets of excitation. So here we kind of see a little wavelets, a little bit on the weaker side. The same thing can happen if chloride comes in. We get instead a wavelet of inhibition, where it's going down. We're getting more hyperpolarized. So these things can happen and do happen all the time. So you get both the up and the down kind of hovering around whatever the resting potential is, and it's only if and only if we reach the threshold that first voltage gate will open on the axon, and that's judged by the axon hillock. So the axon hillock integrates, right? And summates. It puts all of this information together. So remember, that's the integration zone. And the axon hillock basically is adding up the positives and negatives to determine whether or not threshold has been reached. So this to remind you that most neurons have lots of chatter, right? So there's other neurons. These are different neurons that are forming synapses on the cell body of this neuron. Some of them are exciting that, in other words, letting sodium come in. Others may be allowing chloride ions to come in. And so what we look at is, well, then what's the sum total of that? That's what the axon hillock is judging, whether or not we have enough excitation, or if it's more inhibited, or if it's a lot of excitation, then we'll have an action potential happen. In other words, we'll open that first voltage-gated sodium channel. We looked at this too recently, so we saw the fact that that activity or synapses can take a lot of different forms. We can see that in some cases we have multiple inputs here, like the picture we saw just before, where this would be similar to those sort of wavelets of excitation. They all come together and we hit threshold. So these excitatory postsynaptic potentials can take place over different areas on a neuron, so we call that spatial summation. It also can take place over a fairly narrow time point. So if you have rapid fire activity on one area, then we can also reach threshold. So this would also be wavelets, but they're coming in very quickly, and therefore those excitatory postsynaptic potentials cause us to reach threshold, and then there's an action potential. So this is the sort of the picture we see when we're seeing what we looked at before. It's that idea of propagating a signal moving down the axon, and if it's a myelinated axon, literally jumping from a node on that axon where these channels would be to another node. So we're seeing that activity. Here's just, I like this picture because it just shows you how many synapses, in this case, all these little bright spots here are synapses onto a single postsynaptic neuron from other neurons in the brain of a mouse. So this is an actual photograph here. We know this diagram very well. So we have, here's these right here. You see these little blips right there. Those would represent on this graph little wavelets of excitation, or excitatory postsynaptic potentials, EPSPs. But if you have enough where the stimulus is sufficient, either spatially or temporally, to reach threshold, then we get first voltage gated sodium channel opens, sodium floods in, the neuron is depolarizing, followed by those channels, those voltage gates locking, and the corresponding potassium gates in response actually to what happens here voltage-wise will open. Potassium leaves the cell and actually hyperpolarizes, so that eventually it has to be brought back up to resting state by the sodium-potassium pump. This is a nice picture just to show, sort of from the time standpoint. So first we're going to get sodium coming in, then we get sodium is going to be kicked out, potassium's going to be, potassium's going to leave too, right? So we have sodium comes in, followed by potassium leaving, and then this segment of the neuron is getting back to action, to resting state by the sodium-potassium pump. But meanwhile, that activity generated another action potential here, or at least that what we just saw in the graph. So we have voltage-gated sodium channels open, sodium comes in, voltage-gated potassium channels open, potassium goes out. The sodium-potassium pump will then work to reestablish this, and then we go to the next time point, and that's where we see that's finished, and now we're going again. So all of this movement from left to right over time, jumping down the axon, if there's myelin here, is really what the action potential is. So it's a series of those events. This picture shows us some of that. Again, just a new view of it, but it's showing that at each segment, at each point in time, this is occurring. So we have, and here's sort of the overview of it all. Now, the neuron needs to go back to its resting state, and so it has to recover. And we know that action potentials go one way. They go down the axon from our pictures from left to right. But a refractory period is a time where a neuron can no longer really have an action potential, or it would take a lot to cause that. So it's kind of a resting phase. If the neuron absolutely won't open any of those gates, those sodium voltage gates, to have another one, then it's an absolute refractory period. If it's a little bit outside of that time frame, then it means that it takes a really strong stimulus in order to generate another action potential within that time. And so just to look at that again, if we can make this look a little bit bigger, we'll do that right here. So we can see on this, the red, in the red, this is the absolute refractory period, meaning that the neuron just can't have an action potential at this moment in time. But then when we get over here, this is the time where the potassium is helping to repolarize the neuron, and then here we have what's happening with the sodium-potassium pump. So there is a possibility in this blue range that a neuron can have an action potential. Okay, we saw this already, so this is just a very quick recap. Resting potential. Then we have sodium coming in, and now we have potassium going out, and all of it put together. So a lot of the action potential is really going to be mediated by what happens at these voltage gated sodium channels. So whether or not this is going to happen at all. But here is what the effect of myelination is. So if we have myelination, the activity is all happening in these little pieces between the myelin. So we're looking at the nodes of Ranvier. And so in effect, even though we have ions on the inside, so here's the axon, but what we see is this more rapid movement down the axon due to the sort of effects of this myelin is causing a quicker activity, and that is the saltatory conduction. So here we go. So myelin unmyelinated neurons will allow activity too. It's just a slower process, and that's because the insulation of myelin isn't there, and so the signal is not as robust, I guess is the best way to say that. So it still moves, but not as easily. There's some electrical principles we could look at in this, but just know that unmyelinated neurons are slower. Then we're going to get into the synaptic transmission. You know a lot about this, but I think I'll save this for the next mini video.